Great. Thanks, Lauren, and thanks, Jeremy, for a good presentation. Um, so I'm Mike George. I'm going to give you a brief introduction for the next talk, which is a topic that's near and dear to my heart, which is the scour of rock masses. I've been with BGC about 9 years now, but I've spent nearly the entirety of my 20 plus years career as a researcher and practitioner, examining erodibility of rock spillways and dam foundations. The 2017 Oroville spillway incident that occurred in California at the tallest dam in the United States, perhaps you guys have heard about it, sent shockwaves through the dam safety community and really put a spotlight on rock scour issues. Scour has historically been approached from a hydraulics perspective, while the rock mass side of the equation has often been underrepresented. And as many of us know, understanding and representing the geology and the underlying geologic structure is key, as water often finds and exploits the weakest link. So we're really excited to be able to present to you some of the state-of-the-art work we're doing to improve the predictive capability for scour during spill events. And so with that, it's my pleasure to introduce our speaker, Dr. Luke Weidner, who has been a real driving force behind this work and making things happen well beyond my capabilities. I think I've told Luke more than once that he's literally making my dreams come true. But about Luke, he received his PhD in geological engineering from the Colorado School of Mines and specializes in assessing geologic hazards using remote sensing and numerical modeling. His experience includes design of monitoring systems and campaigns for remote mapping of natural hazards using laser scanning, photogrammetry, INSAR, and other specialized methods, while his field experience includes landslide and rockfall inspections and assessments throughout North America. And so without further ado, I give you Dr. Luke Weidner.
Thanks, Mike. Can you hear me?
Yep.
Okay, cool. Awesome. Thanks, Mike. Yeah, so the title of my presentation is Simulating Scour of 3D Blocky Rock Masses. I'd also like to acknowledge Daley Clowen, who is also instrumental in making this work happen as well. So as Mike mentioned in the introduction, unlined rock spillways are channels constructed directly from or directly on natural rock formations. And their purpose is to convey excess water from reservoirs or dams during high flow events, such as heavy rainfall or snowmelt. Unlike lined spillways, which have concrete or other protective linings, unlined rock spillways rely on the rock's inherent resistance to erosion. And again, as Mike mentioned, we can consider the Oroville Dam, which is the tallest dam in the United States. And in 2017, nearly 200,000 downstream residents had to be evacuated due to observed rapid headward erosion of the emergency spillway, which had never been before put into use. Examples like this raise critical questions, such as, is scour a plausible failure mode for other dams and infrastructure? And further, how does rock structure in terms of joint density and orientation influence erosion potential? So understanding these factors is essential for ensuring the safety and reliability of unlined rock spillways. There have been many previous studies conducted to investigate this, and the images shown on the screen just illustrate a number of examples of techniques that have been tried to study and better understand rock erosion as a phenomenon. The previous studies that have been conducted predominantly focus on cubic or rectangular prism blocks to represent the rock mass, and that's evident in pretty much every example we've shown here. However, it's important to note that obviously in reality, rock blocks are much more complex 3D shapes, and we know from the Oroville incident and other examples that this can significantly influence erosion patterns. So these photos depict certain investigations that were completed at the Oroville incident in 2017, and observations showed that rock discontinuities played a critical role in erosion behavior. So the examples shown are the yellow polygons show planar features, and the blue polygon shows wedges that are interpreted to have been removed by the power of eroding water. The annotations highlight how discontinuities led to wedge failures, which would not be accurately reflected by cubic blocks. So observations like these have inspired laboratory and in situ prototype experiments to further quantitatively investigate how this happens and what the influence could be. An example in the upper right shows the relationship between the block rotation angle and erosive water velocity for a laboratory tetrahedral block specimen. And this shows that there is a significant influence of the rotation angle of the 3D block, and that is, of course, controlled by the discontinuities. Other field experiments involved instrumented 3D non-prismatic blocks, and here we see a spillway discharging over a couple of these blocks that were equipped with instruments to measure their displacement. In terms of numerical modeling and how we can use this in engineering practice, recent advancements in the last few years have enabled simulating the full interaction between water and 3D rock blocks. However, modeling a single block on a national lab supercomputer takes about a week using a method like this, making it impractical to simulate thousands of blocks at the scale of an entire spillway such as Oroville. Our goal is to both account for the 3D shape of blocks and extend the simulation to encompass thousands of blocks across an entire spillway in such a way that it's practical to apply in engineering projects. So this slide provides an overview of the software that we developed. The software interfaces between the discrete fracture network, which is generated to create the block system representing the rock mass, and it interfaces with Flow3D, which simulates water flow. The main components of the software basically include, it computes a limit equilibrium stability for each block. So we start by generating the blocks using this open source DFN code, just cited here. The block stability software then identifies which of these blocks are removable based on kinematic criteria. And then it assesses their stability using limit equilibrium. And then it creates a watertight surface of the exterior based on which blocks are stable and unstable. This surface is then subsequently passed to Flow3D, which computes the flow velocity for the model surface. And that flow velocity and other information is then passed back into the stability software for iteration on the next step. And so this becomes a feedback loop where the surface geometry is updated and then the flow velocity is updated, etc. To assess kinematic stability, kinematic removability for each block in an automatic manner, because in this case, there's thousands and thousands of blocks, we implemented the Goodman and Shi 1985 3D block theory for removability. And so the illustration on the right shows how we can just, at the click of a button, evaluate all of the blocks that could be removable based on kinematic criteria, so they're not pinned essentially. The limit equilibrium stability module then estimates the hydraulic pressures in each joint and computes a resultant force for blocks that were estimated as removable. And so those forces then act to lift the blocks. If the force is sufficient based on limit equilibrium criteria, then it's removed. The joint pressure coefficients are input properties selected based on experimentally derived values. And it's important to note that using an analytical stability method such as this to remove blocks is an important part of the step, because it is extremely computationally efficient compared to something like a finite difference numerical method. So when we have this full block system of something like 6,000 to 10,000 blocks in a simulated rock mass, that block system is stored as vertices and faces and sort of idealized vector polyhedrons. However, when interfacing with Flow3D and other programs, we convert the block system into discretized volumes of voxels, which is a voxel is the 3D equivalent of a pixel, as illustrated in the bottom center here. This allows us to quickly import something like geotechnical properties to different regions and critically extract an exterior watertight surface, which is required in order to flow water over something. It needs to be watertight. Using voxels as an interface between Flow3D and the block system also allows us to easily update the exterior surface based on which blocks have been removed by erosion. So in this example, if we've identified that this block is sufficiently unstable that it's going to be removed in the next iteration, we can simply identify which voxels are within that eroded block, remove those voxels, and then create a second updated mesh of the exterior surface. So at each iteration of this surface, we use Flow3D, which is computational fluid dynamics software, to compute water velocities and other properties along the surface. For each surface that's analyzed, the simulation is advanced to steady state. And then at steady state, we extract velocity vectors and depth averaged velocity data. I'm wondering if, oh, there it goes. As illustrated by the animation, we can visualize one of these simulations of water flowing over the slope. And in this hypothetical example, some blocks have already been removed. And these depth averaged velocities, which are varying based on the position in the stair-stepping waterfall, those would then be back input into the stability calculation, and the surface would then be updated. The next two slides illustrate a series of 5 erosion steps for a hypothetical spillway slope and the rock mass system shown on the right. We can see how the model is able to simulate progressive upslope erosion of blocks. This upward progression happens because blocks either become removable or unstable after an adjacent block is removed in a previous iteration. In other words, the block at the bottom has to be eroded first, in this case, before subsequent blocks are mechanically able to be removed. The second example here was created by simply rotating the fracture network by 45 degrees. This illustrates that we can easily modify the input DFN to test multiple design scenarios. Now, obviously, we don't have control over the orientation of the discontinuities, but this is just a different way of saying, what if the spillway was designed differently with relative to those discontinuities? And then that enables us to ask questions such as, how does the spillway orientation influence, or how does that influence erodibility with respect to the discontinuities? So moving forward, our aim is to continue developing this method, adding more necessary features, validating it with experiments critically, and making it more user-friendly. In particular, we are adding methods to specify boundary conditions more precisely, obtain better estimates of these critical pressure coefficients through both numerical and physical experiments. We also plan to integrate our code into Flow3D directly, whereas right now it's a standalone system, and that would enable much more rapid prototyping and ease of use. Other opportunities for improvement include incorporating more complex initial surfaces and 3D geological conditions. We'll also be exploring the use of machine learning to assign pressure coefficients automatically based on the local flow conditions and block geometry. So in conclusion, the framework I've demonstrated here enables more efficient scour modeling for 3D rock masses at scale. It thus has the potential to enhance our ability to predict and mitigate erosion in unlined rock spillways, and ultimately could improve dam safety. So with that, I'll thank you very much for your attention, and I put the contact slide here at the end. There we go.